Welcome everyone to the afternoon session. And the first talk will be the second talk of Andrew Long about thermal pressure on ultra-relativistic bubble walls. Please start.
Thanks. Get my water. Yeah, so you may recall that yesterday I spoke about generating gravitational waves from plasma effects in the early universe, and the plan for today is totally different. We're going to be thinking about the speed of bubble walls at first-order cosmological phase transitions in the early universe. So we've already had a few talks on cosmological phase transitions and first-order phase transitions, but just to refresh everybody on that, we're thinking about the early universe, and as the universe expands, the plasma contained within it cools down. And as the plasma temperature drops through the various different energy scales associated with elementary particle physics, cosmological phase transitions may have occurred, associated either with hypothetical beyond the standard model physics like Guts and SUSY breaking, or associated with standard model physics like Electroweak and QCD scales. So we heard from Tanmay, for example, this morning about some of the cosmological relics that can arise from Gut or Electroweak scale cosmological phase transitions. And when we talk about a first-order cosmological phase transition, first-order phase transitions are characterized by phase coexistence. So, for example, in the condensation of gaseous water vapor into liquid water, the formation of droplets are an example of phase coexistence. There's a region of space in which the H2O is liquid, and there's a region of space where it's gaseous at the same time. In the standard model, both the Electroweak phase transition and QCD phase transitions are predicted to be continuous crossovers, not first-order phase transitions, which means that new physics is necessarily required if there was a first-order cosmological phase transition in our past cosmic history, in the universe that we're living in today. And so when we have various different observational probes of first-order phase transitions, these are telling us something about physics beyond the standard model. So it's a rich playground for learning more about beyond the standard model physics. As I said, we're going to be thinking about first-order phase transitions here, which are characterized by phase coexistence. Namely, there's some boundary in the system that separates different phase domains. And we call that boundary a bubble, or we can call that boundary a domain wall. And the story of a first-order phase transition is shown here. The system is prepared in some initial phase, typically a phase at high temperature in which some symmetry is restored, electroweak symmetry, for example. And as the system is allowed to cool, bubbles of another phase, typically a phase in which the symmetry is broken, begin to nucleate. And those bubbles grow, and meanwhile other bubbles are also nucleating. And eventually the bubbles find one another and merge, and the system is entirely filled with the broken phase at the end. The phase transition is then complete. Typically, a first-order phase transition occurs in much less than just one Hubble time. So there's a lot of rich dynamics to study associated with first-order cosmological phase transitions and various different interesting cosmological relics that they could produce. But the story for today is predominantly going to be about how fast do these bubbles grow, or what is the speed of the bubble walls. Why would we care about the speed of the bubble walls? Well, as I was just saying, there's a variety of different relics that can be produced from these phase transitions. I mean, if you think about it, how are we going to learn about a cosmological phase transition that happened in the first fractions of a second after the Big Bang? We're not going to go back in a time machine and watch it happening. We're not even going to recreate the conditions of it in a laboratory because the temperatures and densities involved are far too high. So the only way in which you could hope to learn about cosmological phase transitions is through the other cosmological relics that they produce and might leave behind in the universe today. So some examples include gravitational wave radiation that we heard about from several talks, in particular Ryusuke's talk. We heard about, we could also generate cosmological magnetic fields. We heard a bit about that from Tanmay's talk. And other cosmological relics, primordial black holes, dark matter, particle asymmetries like the baryon asymmetry of the universe, may have all been generated at first-order cosmological phase transitions in the early universe. And in order to derive robust predictions for these various observables, you need to have a handle on, for example, the speed of the bubble walls. It affects the the speed of the bubble walls impacts the spectra of, and abundances of these various relics. So in order to understand how fast the bubbles are going, we need an equation of motion for the bubble walls. And we don't have to look very far for this. I mean, it's basically just F equals ma. You've got a bubble wall. We're going to imagine it's planar because the bubble has expanded enough so that we're looking at a small patch of effectively planar bubble wall. It's getting pushed, and the equation of motion for its motion is F equals ma. If we divide both sides of the equation by area, force per unit area is pressure, and mass per unit area is tension. So then, and VW dot is just the acceleration. So F equals ma can be re-expressed in this way. The non-trivial part is to figure out what are the forces acting on the wall. So there's a vacuum pressure, which we'll talk more about in just a second, that's inducing the walls to, the bubbles to expand. And there's some thermal pressure, which encodes the interactions of the bubbles with the ambient environment, the plasma or medium into which they're immersed. Thermal pressure is effectively a friction force, which may also depend upon the speed at which the walls are moving. And so what we're going to do now is consider some simplifying cases in order to study the solutions of these equations. So to begin, let's suppose that the bubbles are immersed they're just in vacuum. There's no medium around, or at least if there is a medium around, it's very dilute such that the thermal pressure can be ignored. And let's study what happens in that situation. So here I'm drawing a bubble, and we're going to imagine that as we move across the wall, some scalar field phi changes values. So for example, outside of the bubble, in front of the wall, the scalar field takes a value phi s, and inside of the bubble, the scalar field takes a value phi h. The value of the effective potential at phi s is Vs, and so the energy density of the system in front of the wall is also Vs. Since the system is in vacuum, the equation of state is -1. So the pressure in front of the wall is negative Vs. On the other hand, behind the wall, inside the bubble, the energy density is Vh, it's a bit smaller, and so the pressure is negative Vh, it's a bit bigger. And so there's a pressure differential across the wall that's making the bubble want to grow. So we can put that into our formula, our F equals ma equation, setting the vacuum pressure equal to the tension times the acceleration, where the vacuum pressure is just the difference of Vs and Vh from the previous slide. And solving gives linear growth in the speed of the wall, where pvac over sigma is the acceleration. Of course, if you take this formula literally, the wall will reach and exceed the speed of light in finite time. In fact, it'll get up to the speed of light in a time tau, which is c sigma over pvac. Of course, the wall doesn't actually reach and exceed the speed of light. The formulas no longer work once the motion becomes relativistic, and we should instead be solving F equals ma in its relativistic form. And of course, as you'd expect, under a constant acceleration, the speed of the wall grows linearly in time at first, and eventually asymptotes towards c. And the associated Lorentz factor, which is going to play a big role throughout the rest of the presentation, just given by 1 over the square root of the speed squared, starts out at 1 and then grows linearly with time as the bubble continues to accelerate. The v is approaching c, but the Lorentz factor is continuing to grow. This time tau then is essentially how long it took for the bubble to accelerate up to relativistic speeds. And you can do some simple estimates and convince yourself that it doesn't take very long for the bubble to get up to these relativistic speeds. Much less than a Hubble time, the bubble will typically be moving close to the speed of light if there's no medium around and it's moving in vacuum. So that situation is known as a runaway, in which only vacuum pressure is inducing the bubble to grow, and its speed asymptotes to the speed of light, where the Lorentz factor continues to grow without bound. Now, that's the dynamics when the thermal pressure can be neglected. What about the totally other regime, where the thermal pressure is large and playing an important role, in which the bubble now is sort of tightly coupled to the medium? So in this regime, the system is now very nonlinear. The vacuum pressure is still inducing the bubble to want to grow, but the bubble is pushing on the fluid. The fluid is flowing out in front of the bubble as a sound wave, like we heard about from Ryusuke's talk on Tuesday. And moreover, that sound wave and the fluid is exerting a drag force back on the bubble. The evolution of the joint, the two-body system, so to speak, between the bubbles and the fluid now is very nonlinear. And so often numerical methods like numerical lattice simulation are used in order to study the associated dynamics. And in fact, these types of simulations are required in order to derive robust predictions for the various observables associated with these first-order phase transitions, things like the spectra of gravitational waves or the viability of baryogenesis at the bubble walls. So we've already had a couple of talks about this topic, and I think we're going to hear more about it over the next week or so. I'm not really going to discuss this regime any further. It's complicated. And what I'm looking for instead is a middle ground in which we're going to calculate the impact of the medium or the fluid or the plasma. We're going to calculate its impact on the dynamics of the bubble wall through the thermal pressure, but we want to find a regime that's analytically tractable. Not necessarily because that's the one that's most likely to be realized in nature, it's just the one that I can actually work out without having to use a supercomputer. And there is an analytically tractable regime. It's one in which the bubble walls are moving ultra-relativistically. Imagine that the vacuum pressure has gotten the bubbles moving real fast, much faster than the speed of sound in the plasma. The speed of sound is usually around 1/√3 for a relativistic plasma. And if the walls are moving much faster than that, then the fluid and plasma in front of the wall doesn't know that the wall is coming. The particles in the plasma there are living in their Bose-Einstein or Fermi-Dirac phase space distribution functions, ignorant of the fact that a big wall is about to smack into them. And when the wall does encounter a bubble, the time it takes for the bubble to transit across the particle is really short compared to any other timescales associated with the response of the fluid. So in this regime, we'll be able to think about thermal pressure by considering individual particles hitting the wall rather than having to keep track of the fluid as a whole. So the whole rest of the talk is going to be about calculating the thermal pressure in this particular regime. And there's been a lot of work on that problem over the last almost a decade, I guess, starting with this landmark paper by Dietrich Bodecker and Guy Moore in 2009. They revisited the problem in 2017, somewhat revising their conclusions, or extending, I guess I should say, their conclusions. And that got my collaborators and I interested in this problem. So we wrote a paper, we studied it around the same time and then wrote a paper in 2020. And there has been since a kind of explosion of interest in Electroweak bubble walls and their speed. This is not a comprehensive list of references, so I apologize if things are missing. There was also some amount of confusion about some of the conclusions of our paper, at least judging from all the emails I got at the time. And so one of my collaborators, Jessica Turner, and I revisited the problem over the last year or so and put out a paper last summer where we tried to clarify some of the confusions. So one of my goals for this presentation is to hopefully clear up some of the confusing things. Now, I appreciate that this audience, if many of you may not be familiar with the confusing things in the first place, so it may be lost to you. But I think I'm going to try and walk through systematically, basically the rest of the presentation is me telling you what happened in the Bodecker-Moore 2009 paper, what changed in the 2017 paper, and then the approach that my collaborators and I were using and how to reconcile the different results. So that's the plan for the rest of the talk. All right, so any questions about that before I get going? Let's begin by discussing the Bodecker-Moore 2009 paper, where they were studying what we now call one-to-one transitions. And here, again, we're imagining one of these ultra-relativistic bubble walls moving through the plasma. And we're going to think about a particle in the plasma whose mass changes across the wall. So in front of the wall, the particle has a mass ms, but behind the wall, the particle has a mass mh. And we're going to think about this particle interacting with the wall. We're going to do this not in the rest frame of the plasma, but it's easier to work in the rest frame of the wall. So here my wall sits at rest, and there's a particle incident on the wall that passes through, and it changes its momentum a little bit, recoiling with a momentum pH. So since in this frame the wall is at rest, time translation invariance gives us energy conservation, and the system approximating the wall as planar gives us translational invariance in the two directions transverse to the wall or along the wall. So transverse momentum conservation. We have also transverse momentum conservation, and the particle remains on shell. So what's happening is as the particle gains some mass, it has to lose some longitudinal momentum in order to maintain these conditions. And the longitudinal momentum lost by the particle is compensated by the longitudinal momentum change of the wall itself. That's why there's a pressure. And you can calculate the longitudinal momentum change of the particle. When we do these calculations, since we're in the restroom of the wall, but the wall was moving really fast relative to the plasma, it means that the plasma is incident on the wall with a huge boost. So in the rest frame of the plasma, you grab a particle, and it'll probably have a momentum and energy around T, the temperature. But in the rest frame of the wall, the particles have much larger energy because they're boosted up to gamma T. So in this frame, we can then expand these expressions for large E, and it reduces down to this, where the momentum transfer is just the difference of the squared masses over gamma T, dropping the factor of 2. It's not terribly important. Now we know a bit about the kinematics of particles hitting the wall. What's the pressure? So the thermal pressure then can be calculated in this way. We need to use the phase space distribution function for that particle hitting the wall. Particles hitting the wall are drawn from a Bose-Einstein or Fermi-Dirac distribution, depending on their quantum statistics. So that's showing up here. Nu is just a multiplicity factor. It's 2 for spin, it's 3 for color, it's the usual thing. And we're weighting this integral by the momentum transfer. So this first bit is effectively just the flux of particles onto the wall. It's got units of per area per time. And again, because of the fact that the particles are boosted onto the wall, it's enhanced by a factor of gamma. The V is basically a 1 because V is C and C is 1. But it's important that the flux is enhanced by a factor of gamma. And the momentum transfer in this calculation then is just given by the formula from the previous slide. You'll notice that the factors of gamma now cancel. If the wall were faster and faster and the Lorentz factor were higher and higher, the flux would be getting bigger and bigger, but the momentum transfer would be getting smaller and smaller. And so the thermal pressure, when we put the two factors together, then just scales like the difference of the masses squared times the temperature squared. It doesn't care about the speed of the walls in this regime, just like the vacuum pressure from the example a couple pages ago. And so when we put this all back into F equals ma, and we can ask, well, what would happen if the vacuum pressure were bigger than the thermal pressure, depending on the parameters and how much the mass changes and what's the latent heat of the phase transition or the vacuum energy difference. It may be the case that the vacuum pressure is bigger than the thermal pressure. Then you would find that, just like before, the bubble wall will run away. VW will grow up towards C, and the Lorentz factor will grow without bound. And so this was the conclusion of Boddicker and Moore 2009. And it featured prominently in some later phenomenological studies. So for example, one of the working groups for LISA, the space-based gravitational wave interferometer, they put out a report in 2015 where they were describing the different ways in which you might get first gravitational waves from first order phase transitions, such as the Electroweak phase transition. And you can see here I'm highlighting section 2.2, where they're giving these 3 cases, which are basically what we've just discussed. They say you could have a runaway bubble in vacuum, which was the first thing we discussed. You could have a runaway bubble in a plasma, which is what we're discussing here. Or you could have a non-runaway bubble, which is the situation where the thermal pressure is larger than the vacuum pressure. If that happens, the bubble doesn't reach ultra-relativistic velocities. It saturates to some non-relativistic velocity. It's like that tight coupling regime that we were talking about earlier. So that was the situation in 2015. But Boddicker and Moore strike back in 2017, where they studied what we now call 1-to-2 transitions. I guess maybe they called them 1-to-2 transitions. And here the idea is that when a particle hits the wall, it may not simply pass through the wall. It may, by doing so, emit another particle or split into a pair of particles. So here are just 2 examples. You can imagine that a quark, maybe an up quark, passes through the wall, converting into a down quark and emitting a W boson. Or you can imagine that maybe an electron hits the wall and remains an electron, but by doing so, it emits a photon. So this is like a transition radiation that's induced by the particles getting a jiggle as they're going through the wall due to their mass change. This turns out to make, on the one hand, the calculation technically much more complicated. So to get organized, the first thing we're going to have to do is add some labels, because now there's 3 particles involved, and they may have different flavors. So we'll add a flavor label, A, B, C, to distinguish the 3 types of particles. But the real reason life gets more complicated is because of this. Now when we go to calculate the thermal pressure, we're going to be doing a similar thing as before, where we're integrating over the phase space of the incident particles and multiplying by a momentum transfer. But the thing is, the momentum transfer is no longer deterministically determined. But instead, when we shoot that particle in, it's a quantum random process that determines the momentum of the recoiling particles. I send an electron in, and quantum mechanics tells me whether I recoil an electron like that and a photon like that, or a photon like that and an electron like that. And so we have to calculate, instead of just a momentum transfer, but we're calculating this quantum expectation value of the longitudinal momentum transfer by weighting the momentum transfer among the 3 particles with the probability for a particular final state phase space. And that's where the calculation becomes more tricky. And so, well, on the one hand, let me say one thing. So at this point, we're kind of shifting the problem. So it's no longer our goal to calculate the thermal pressure. Really, we should think of our goal now as calculating the longitudinal momentum transfer. Because if we can, these first factors in greenish are really just gamma t cubed. So we already know how to handle these flux factors in the front. The new challenge is for us to calculate the average longitudinal momentum transfer. And then getting the thermal pressure from there is almost trivial. All right, so how are we going to calculate the average longitudinal momentum transfer, blah, blah, blah. So anyway, we need to get this probability. And there's 2 approaches that have been discussed in the literature for how to calculate this probability. In order to talk about them, my collaborator and I gave them names. So the approach that was used by Boddicker and Moore 2017, my collaborator and I are calling the quantum particle splitting formalism. They don't call it that, but it's just a name for what they've done. And I'll describe that next. Whereas in the papers that I was working on in both 2020 and 2024, we used another approach that we are calling the semi-classical current radiation formalism, and I'll describe that afterwards. And we'll compare the 2 and see in which regimes do they agree and give the same answer, and when do they give different answers. So first, let's talk about, since we're talking about Boddicker-Moore 2017, that's the current section of the talk, let's discuss how they did the calculation. So they said, let's calculate the splitting probability using this formula. And it looks a bit nasty, but it should also look a bit familiar, because it's the same sort of way we calculate decay rates or scattering cross sections in QFT, just with some subtle minor modifications. So here's the usual Lorentz invariant phase space factors that we know and love. Here's the energy momentum conserving Dirac deltas that we know and love, except remember that longitudinal momentum is not conserved. And so we're only getting, so the system is actually not, yeah, so longitudinal momentum is not conserved. So rather than getting 4 Dirac deltas, we're getting 3 Dirac deltas associated with energy and just transverse momentum conservation. And here's the matrix element, which is now not a Lorentz invariant matrix element, because again, we're doing this calculation on the background of a varying mass. So the system does not have spatial translation invariance in the direction normal to the wall. Anyway, so as I said, it looks scary at first, but if you recognize that it's similar to QFT stuff, it's not so scary. But then if you start to dig in, it's a little scary again, because there's some subtle distinctions in there. For what? Yeah, so you're asking if they're included, or should they be included? They are not included. The idea is that since the wall is moving so fast, the particles behind the wall they're not bunching up behind the wall, they're just getting left behind as the wall passes by. So one doesn't expect occupation numbers to get comparable to 1. I mean, you could include them, but it wouldn't impact the answer. The wall is just assumed to remain planar, it's not excited. I mean, the wall, I mean, as the bubble grows, I think it'll want to smooth, right? Even if you imagine that when the bubble nucleates, it's not a perfect sphere. As it grows, it'll tend to sphericalize. So I imagine that I imagine it should be fine. But also, I mean, you know, for these calculations, we're treating the wall as perfectly planar. But of course, it's not planar. It's a bubble that's growing. But you know, for a sufficiently small chunk of the wall, it's reasonable to treat it as planar for these calculations. There are evidences of other particle species stuck to the wall? You're talking about ripples on the wall. Is that what you mean by bound states? Okay, well, I guess, yeah, I hadn't thought about that. So I'm imagining that the wall is just planar and smooth. I'm sorry? Yeah, it is a fixed background. It's treated to be a fixed background. The typical one? Mass scale of the wall with? We can. I don't know if that answers Tanmei's question, but maybe we should come back to it afterwards. I mean, I'll give some numerical answers for the momentum. I mean, I'm going to talk about the momentum transfer and that sort of stuff. So maybe it'll be clear when I get to that part. It's not obvious to me that it's going to answer Tanmei's question. But are there other questions while we're stopped? I have a slide on that. Okay, very good. So, and then the last bit to say is that actually evaluating this matrix element is also a little tricky because of the wall, the mode functions for the particles whose masses change there are not just plane waves anymore because the mass changes. So the mode function is modulated. You can calculate that using WKB approximation. So all of that has to be factored in when you evaluate this expression. And I'm not going to show you how to do that. If you're interested, you're welcome to take a look at Lodecker and Moore's paper. My papers also have a summary of how to do these calculations. So I encourage you to check it out there. Let me just give you some of the answers. So if we're in this regime where we have a massless radiator, so let's consider a couple simple examples. Okay, there can be lots and lots of different scenarios, but we're going to consider here and throughout the rest of the talk just two scenarios. So scenario one is a massless radiator emitting massive radiation. So this would be like a quark that I'm treating as massless that passes into the bubble and becomes a different flavor of quark that also I'm treating as massless, but emits a massive W boson. And if you take that as your input and go through a whole bunch of math, you'll arrive at this expression for the average longitudinal momentum transfer. And it kind of makes sense. So remember, there's a squared matrix element on the previous page, so we expect to find a coupling squared. This is a quadratic Casimir that also goes with the coupling. So that factor looks familiar. These factors depend on the mass of the radiation particle, in this case, W. And you can check that if the mass of that particle does not change, so MCS is equal to MCH, then the factor in parentheses is 0. So if the radiator particle does not change mass and the radiation particle does not change mass, then really nothing happened when you went through the wall, and there would be no momentum transfer and there'd be no pressure. It turns out there's an IR divergence when you integrate over the momentum of this W boson, but it's cut off by one of these masses, whichever one's smaller. If the mass is growing as you enter the bubble, then this thing in the denominator is MCS. All right, very good. So now, is that a question? This is just as I said, for illustrative purposes, let's consider this scenario. You're welcome to consider a more general case in which I have tops and bottoms and the mass change is very appreciable. But if you imagine that the two quarks are maybe U's and D's and then their masses inside the bubble are still negligible compared to the mass of a W inside the bubble, that's a regime in which this calculation is more relevant. So now as a second example, let's suppose that we have a massive radiator particle that emits massless radiation. So here I've got it could be electron to electron plus photon, where the electron mass goes up as we enter the bubble, but the photon mass just remains 0 on both sides of the wall. And if you go through another lengthy calculation, you'll arrive at this formula for the average longitudinal momentum transfer. And it has the nice appealing feature as before. It goes like coupling squared. This factor vanishes if the masses are unchanged across the wall. Now there's a logarithmic, both UV and IR singularity associated with this photon momentum integral. So that's captured over here. But also, somewhat importantly, there's a factor of EA in the denominator. That's the energy of the incident electron. And remember that EA in the restroom of the wall is always up at order gamma T. That's what this stuff on the board was for. So if we were to ask about the different gamma scalings in these two calculations, the calculation in the bottom would have a longitudinal momentum transfer scaling like gamma to the -1, but the calculation at the top would have it scaling like gamma to the 0. And so since the thermal pressure is the momentum transfer times an extra flux factor with one more gamma, in the bottom case, we get thermal pressure scaling like gamma to the 0, which was the same thing we had encountered in Boddicker-Moore 2009. It was the same as the vacuum calculation. But in this top example, where the emission of a massive spin 1, you have the emission of a massive spin 1 particle, the thermal pressure instead scales like gamma to the 1. And this was really the key conclusion of Boddicker-Moore 2017. They pointed out that when you account for these 2 to 3 processes and specifically consider channels with massive spin 1 radiation, then the thermal pressure actually grows as the bubble speeds up. And what that means is that eventually the thermal pressure will come up to meet the vacuum pressure, and then they'll balance. And at that point, subsequently, the bubble will only expand at a terminal velocity. Any subsequent liberation of latent heat doesn't go into accelerating the wall, it goes into pushing around the fluid. And this is important, for example, for the gravitational wave calculations, because as we heard from Yusuke and others, the spectra of the gravitational waves that you get from the bubble colliding versus the spectra you get from the sound shells colliding are different. Okay, so that's all kind of summarized here. You know, Boddicker and Moore were using this quantum particle splitting formalism. If you consider massless radiators emitting massive radiation, you'll arrive at the novel result that the thermal pressure scales like gamma to the 1, and therefore bubbles can reach an ultra-relativistic terminal velocity. The terminal velocity is still very big, by the way. It's not like it's a terminal velocity of 0.1 c. It's still a high Lorentz factor. On the other hand, if you were to consider a channel in which the pressure is dominated by a massive radiator emitting massless radiation, then you'd find that the thermal pressure would scale like gamma to the 0. All right, very good. So finally, let me talk about what our contributions were, but both in 2020 and now 2024. So I'm just going to read this big wall of text to you because it tells you a little bit about how we got into this. So we were motivated by Boddicker-Moore 2017 to start thinking about electroweak bubble wall velocities, and we suspected that we noticed the IR sensitivity in the calculations from Boddicker and Moore and suspected that this would require a resummation of multiple soft emissions in order to get a reliable result. So we set out to extend their calculation of 1 to 2 scattering into 1 to 3, 1 to 4, 1 to many scattering, and then resum all of those different channels with multiple soft emissions. We weren't able to formulate that calculation using the QPS formalism that Boddicker and Moore employed, and so we adopted this alternative, what I'm calling semi-classical current radiation formalism, in order to actually evaluate these multiple emissions. And so we succeeded by using that formalism, resumming all the soft emissions, and our result, having done that, was different from what Boddicker and Moore found. We got instead that the average momentum transfer went like gamma to the 1, and therefore the thermal pressure went like gamma to the 2. And we found that regardless of whether it was a massive radiator case or a massless radiator case. And as I said, I know earlier when I was introducing the literature that this led to some confusion and led to a bunch of emails and things. And so, you know, part of the confusion, I think, was that we were really doing 2 things differently from Boddicker-Moore 2017. We were adopting this SCR formalism rather than the QPS formalism, and also we were doing this resummation. And we didn't make it terribly clear, I suppose, in the drafting of the paper, which of the 2 things is what led to this different result. So what we've done in the new paper with Jessica Turner is try to make the situation more clear, and I'm going to explain it to you now. All right, so what is the semi-classical current radiation formalism? So for this and the rest of the whole talk, we're only going to be thinking about the massless radiation case. So we're thinking about say an electron, or it could be a top quark, it doesn't matter, enters the bubble and gains mass, but emits a massless particle like a photon. And we're treating that radiating particle as a classical current. So for example, here's the world line for the electron, where it's moving along at a constant speed, and it encounters the bubble wall represented by this vertical blue line, and it slows down a bit. And that classical current then, the world line then corresponds to an electromagnetic current density given by this formula. We're just integrating the world line for the particle. On the other hand, the photon, or the electromagnetic radiation, is treated as quantum. So the photon field is still quantized with ladder operators, and then the interactions between the 2 are captured by an interaction of this form, the classical current interacting with the quantum photon field. And the plan now is to calculate the probability we're still looking to calculate the average momentum transfer, but we're going to do the averaging by calculating the probability like this, where this is the probability to emit a single photon having momentum p. W is a matrix element representing the overlap of the no photon state and the one photon state, thanks to the presence of the source. And you could do a little bit of work and you'll arrive at an expression for the matrix element that looks like this, which is the dot product of a Fourier transform of your current density and the polarization vector for the photon. And then by summing over the polarizations of the photon, you arrive at an expression like this for the probability to emit a single photon. It's related to the square of the Fourier transform of the current density. If that looks familiar, it might be because you've already solved this problem. So in Peskin and Schroeder, chapter 2, they do an exercise in which they consider a scalar field with a classical source, and you're asked to calculate the probability of emitting the average number of particles that are emitted. You get the same sort of expression. It's the square of the Fourier transform of the source. So it's a standard approach for evaluating the spectrum of emission from a classical source. So let's compare the two formalisms very quickly. In both cases, we're calculating the average longitudinal momentum transfer by integrating the 3-particle momentum transfer over some probability. But in the quantum particle splitting formalism, the probability is a splitting probability. You pick up incident particle momentum and then calculate a probability distribution over the 2 recoiling particle momenta. That's what is done in the QPS formalism. In the SCR formalism, it's more of an emission probability. So you have to pick both PA and PB, the incident particle momentum and the recoiling charged particle momentum, and then you calculate probability distribution over PC, which is the photon momentum. So that the two situations differ in that regard. Now the question arises, you may be asking, how do you, I think we're good. Excuse me. So the question might arise, how do you decide on PB? And so how should we select PB, which is the momentum of the recoiling electron now inside the bubble? And here's one approach. Let's suppose that the radiation, the photon, is very soft. And so it doesn't carry away a lot of momentum at all. And then the kinematics, the 3-particle kinematics, are basically back to the 1-to-1 kinematics that we initially talked about from Boddacker and Moore 2009. So if the momentum of the photon can be neglected, then we can use the 1-to-1 kinematic that we talked about earlier, and then you go through a lot of work. The work, by the way, if you're interested, you can take a look at the paper. It echoes some of the things that we heard from Ashok Sen earlier this morning, where you're doing some complex analysis, contour integrals, to evaluate these integrals. So it runs a bit parallel to the calculation we heard about this morning. But anyway, you'll arrive at this formula. And this formula should look familiar because it's precisely the same formula that I presented a few slides ago as the result in the quantum particle splitting formalism. In other words, the conclusion here is that you can arrive with this choice of PB, you'll arrive at the same answer for the average momentum transfer and also the thermal pressure that you would have gotten to from the QPS formalism. The two formalisms can be made to agree in this regard. Now, you may have in mind another way of choosing this momentum PB, the momentum of the electron now inside the bubble. Perhaps I want to impose energy and transverse momentum conservation among all 3 particles, as shown over here. And again, if you go through some amount of work, you'll arrive at an answer which is shown here, where the average momentum transfer now is to leading order. I'm dropping higher order on important things, but to leading order, it's a UV divergent quantity when we do the integral over the momentum of the photon. And so the average momentum transfer depends on the cutoff that we use for the momentum of the photon. This is a pretty funny looking formula. I mean, for a couple of reasons. For one thing, there's no mass dependence in here. So even if the mass of the particles did not change across the wall, this formula is telling me that there's still a momentum transfer, which is peculiar. And it also has a strong UV sensitivity, shown over here, such that if I imagine cutting off this momentum integral on the photon using the incident particle energy, gamma t, okay, I'll finish up just one more minute. Oh, thanks. If I cut off the momentum integral on the photon using the incident particle energy, which is gamma t, then I would find that the average momentum transfer scales like gamma to the 1 and the thermal pressure scales like gamma to the 2, which is the same scaling that was reported in our earlier paper. And so the takeaway here is that if one intends to use the semi-classical current formalism, one should take care in choosing the momenta of the incident and recoiling particles, particularly the recoiling particle. Reasonable results are obtained when the one-to-one kinematics are employed and the photon is treated as soft, whereas peculiar results are obtained when the three-particle kinematics are employed. And the last thing I want to say before wrapping up is to address the finite wall thickness. We did a second thing in this more recent paper that I have not really even touched upon as half of the paper, but it's only going to get one slide in this short talk, which is to study also the impact of the finite wall thickness. So on the previous slide, I was saying that the calculation was sensitive to the UV cutoff, which I took to be the incident particle energy. And if the wall were treated as arbitrarily thin, the incident particle energy would be my UV cutoff. But the wall is not arbitrarily thin. It has a finite thickness. In its rest frame, it's LW. And that introduces a new UV cutoff scale. And so that cutoff scale is actually below gamma T. So in reality, when we estimate this maximal momentum for the photons, we shouldn't be using gamma T, but we should instead be using the inverse wall thickness. And so here's some numerical results that we obtained. I mean, they're numerical in the sense that some of the integrals couldn't be performed analytically in the last step, so we just numerically integrated, showing essentially how the probability distribution over the momentum of the photon is essentially flat in a log scale up to roughly this scale, gamma squared over the wall thickness. And that's actually the same result that you'd expect from classical Bremsstrahlung. It's in chapter 15 of Jackson. All right, well, anyways, just to wrap up, by way of summarizing, here's a table from the conclusion section of our paper that gives you all these different results that I've been talking about. Kind of the punchline was that if you're studying models with a massive radiator and massless radiation, you'll arrive at the same answer using either of these two formalisms, which is to say that the thermal pressure scales like gamma to the 0 and a runaway is possible. If you're studying a model with massive radiation, then the Butterker and Moore result from 2017 would still apply. The thermal pressure would scale like gamma to the 1, and the runaway would be prohibited. Instead, you'd reach a terminal velocity. And the other kind of lesson here is to take care if you're employing this semi-classical current formalism, one should take care in choosing PB, the momentum of the particle inside the bubble, because some choices may give, some choices will lead you to find that the thermal pressure scales like gamma squared. I'll be around for the next week, so there's a couple, I mean, I've had a lot of fun on this project over, I guess, the last 4 years. I think I've probably put more work into these two papers than I have into any other single paper I've ever written. So there's a lot of work that went in behind the scenes to writing these papers because I've enjoyed it a lot. So if people are interested in talking more about some of the details of these calculations or directions for future work, I'd be happy to chat over the next week. All right, thank you very much.
Now time for questions.
Because the photon velocity in the plasma would be less than 0.
Yeah. Yeah, I mean, for these calculations, I was neglecting medium effects and plasma masses and that sort of thing, but there would be the possibility of particles propagating faster than the speed of light in the medium, so I suppose there could be Cherenkov radiation. I suppose there could be. I'm not sure. I haven't really thought about it.
So I have one question. So you have told about this thermal pressure and vacuum pressure. So for thermal pressure, you have written the formula. But what about this vacuum pressure, and is it model dependent or not?
The vacuum pressures, the vacuum pressure is model dependent. Thanks for the question. So it's usually, if your phase transition is induced by some scalar field that's tunneling from a metastable vacuum somewhere across the barrier, then the vacuum pressure is the difference in the effective potential on either side in the two different phases. By the way, you may have noticed that this dot is not actually at the minimum, because when the tunneling happens, you don't tunnel all the way down to the new minimum, you just tunnel across the barrier a little bit. And how far you tunnel depends on things like the temperature and the shape of the barrier. So there is a model dependence in getting the vacuum pressure, but it's a little bit easier to study because it's just about the one scalar field that's doing the phase transition. It doesn't depend so much on what all the other different degrees of freedom in the system are all up to.
So is it somehow connected to latent heat? So
To
this
what?
vacuum pressure.
Is it connected to what? Sorry?
Latent heat.
Oh, latent heat. Yeah, it is. It's related to the latent heat. So the latent heat is, I guess, is defined as the energy density difference across the two phases. And so it's linked to the latent heat. Yeah.
And another question is, what about the surface tension of this wall?
So that does impact the dynamics, but once the bubble gets sufficiently large and can be treated as planar, then the surface tension isn't appreciably impacting the dynamics any further.
Okay, thank you.
Yeah, good question.
Okay, so maybe I have a question. So you consider, if I understood correctly, the situation where you, like in the new phase, you have the VAV, which enhances at least some of the masses, right? Have you thought about like the opposite case where like you have initially the VAV at high temperature, but then it loses a VAV? Like so that the particles lose mass.
Yeah, that's a great question. So I only started thinking about that this summer. I think Bibhushan Shakya was asking me about that. There is some, so what can I say? Some of the formulas already apply. So like this formula works fine if ms is larger than mh. It actually indicates there would be a negative momentum transfer because the wall will want to accelerate in order to continue lowering the mass of all these particles. And also you can check in my later formulas what happens if the masses are swapped around. We didn't really discuss it in these papers. There is a discussion of it in one of these two papers, I believe. Maybe this paper, this one? Yeah, it's this one. So there's some discussion there of this, what do you call it, inverse transition or the transitions where the masses go down. Yeah.
Okay.
Yeah.
Thanks. I mean, it's like I work on a model I will talk about on Monday in which something like this happens. So.
Oh, cool. Yeah.
Yeah.
I would chat about that more. Maybe also Bibhushan would be here on Monday.
I have one more question about when you like. Oh yeah, exactly. With the treat at the beginning. With the distribution function, right? So, and one consider the case where this distribution is not thermal, but it's somehow, but it's and can it have an impact or?
I have not thought about it. I mean, since in regard to the gamma W scaling, I don't think it's going to make a difference. I mean, what's important to calculate delta PZ is really just that the incident particle is a Lorentz factor times something. So I mean, even if the distribution in front of the wall weren't thermal, there's some other energy distribution, which is typically P star in the system rest frame. It'll still be gamma P star in the wall rest frame. And so the gamma scaling aspects would all be the same. But you're right that, you know, I was estimating the flux factor as a gamma T cube. It wouldn't be T cube, it would be a P star cube or something now, I imagine.
Okay, thanks. Any more questions? Comments? So let's thank Andrew again.